Good morning. In this lecture we are going to see one-dimensional wave equation and how to find the solution for this with some examples. So before going for wave equation, we are going to see classification of second order linear partial differential equation. The general linear partial differential equation of second order can be rewritten as A dou square du by dou x square plus B dou square du by dou x dou y, C dou square du by dou y square plus D times dou u by dou x plus E times dou u by dou y plus F u equal to 0. And it can be rewritten as A u xx plus B u xy plus C u yy plus D u x plus E u y plus F u equal to 0. And A, B, C, D, E and F are in general functions of x and y. So first identify the coefficient of uxx, which is A, coefficient of uxy, which is B, coefficient of uyy, which is C. Then condition to classify is find b square minus 4ac. If b square minus 4ac is less than 0, then the given equation is classified as elliptic. If b square minus 4ac is equal to 0, then the equation 1 is classified as parabolic. If b square minus 4ac is greater than 0, then the equation 1 is classified as hyperbolic. Example. Consider this example: dou square du by dou x square plus dou square du by dou y square equal to 0. Name of the equation is Laplace equation in 2 dimension. And coefficient of uxx is A, which is 1. And dou square du by dou x dou y term is not there, so coefficient B is taken as 0. Dou square du by dou y square, coefficient is 1. So C is equal to 1. So b square minus 4ac is equal to minus 4, which is less than 0. Therefore the given equation is classified as elliptic equation. Next example, consider this. This is called as one-dimensional heat equation. Coefficient of uxx is A, which is 1, and dou square du by dou x dou t is not available, so B is equal to 0. Dou square du by dou t square is also not available, so C is 0. So b square minus 4ac is equal to 0. Therefore the given equation is parabolic. Since B and C is 0, so we will get this condition is equal to 0. Therefore the given equation is parabolic. Consider another example, which is a one-dimensional wave equation, which is a partial differential equation of order 2. Coefficient of uxx is A, which is 1. B is equal to 0. Dou square du by dou x dou t is not available. Dou square du by dou t square is equal to minus 1 by alpha square. So find b square minus 4ac. B is 0 and substitute what is A and C. We are getting this is 4 by alpha square. So this quantity will be always positive, because even if alpha is negative, alpha square is there, it will become positive. So therefore the given equation is classified as hyperbolic. Next example, dou square du by dou x square plus 2 dou square du by dou x dou y plus dou square du by dou y square equal to 0. A is 1, B is 2 and C is 1. So therefore b square minus 4ac is equal to 0. The equation is parabolic. Next example, this is an important example where A is 1, B is 4, A is 1, B is 4, and C is equal to x square plus 4y square. So far we seen examples where values of A, B, Z are constant. Here in this example it is a function of x, y. So according to the value of x and y, the value of the b square statement b square minus 4ac will vary. So substitute what is b, a, c in this. Simplify, we got 4 into 4 minus x square minus 4y square. So according to what is the region, we will classify the curve as elliptic or hyperbolic or parabolic. So for case 1, so the equation is elliptic, so I am considering that the equation is elliptic. If this equation is supposed to be elliptic, means the condition should be less than 0. So take this condition as less than 0 and rewrite this equation by bringing these two terms to the other side. It will become x square plus 4y square is greater than 4. Bring this 4 to the other side, it will become x square by 4 plus y square by 1, which is greater than 1. If you bring this 4 to the other side, this will become 1. So therefore this is the equation of ellipse whose major axis with meet at the point 2 plus or minus 2, minor axis meet at the point plus or minus 1. So greater than 1 implies that the region is exterior of the ellipse. So the given equation is classified as elliptic in the region outside the ellipse, x squared by 4 plus y squared by 1 equal to 1. So the exterior of the elliptic region, the given equation is classified as elliptic. Next I'm classifying the given equation as hyperbolic. So if it's supposed to be hyperbolic, I should have this condition as b square minus 4ac is greater than 0. So take this expression and put greater than 0, then bring these two terms to the other side and rewrite it. Bring this 4 to the other side. We are getting the condition as x square by 4 plus y square by 1 equal to less than 1. So less than 1 means this is the equation of the ellipse. Less than 1 implies that the region is interior of the ellipse. So it is hyperbolic inside the ellipse. Similarly, it is parabolic on the ellipse. So parabolic means this condition is supposed to be equal to 0. If I equate it to 0 and simplify it, I will get the curve ellipse. So it is parabolic on the ellipse, x squared by 4 plus y squared by 1 equal to 1. Note that the same differential equation may be elliptic in one region, parabolic in another region, hyperbolic in some other region. For example, xu xx plus uyy equal to 0. So a is x, b is 0, c is 1. So b square minus 4ac is equal to minus 4x. So this equation, given equation, is elliptic if x is greater than 0. If x is greater than 0 means this condition will be less than 0. So less than 0 means condition is less than 0 means we will conclude the equation is elliptic. So if x is less than 0, x is negative means the entire term will become positive. So b square minus 4ac is positive means I will classify that given equation as hyperbolic. So if x is equal to 0, the condition will become equal to 0. Then in that case I will classify the given equation as parabolic. Next we are going to see one-dimensional wave equation. So consider the small transverse vibration of an elastic string which is stretched to a length L and then fixed at its two ends O1A. So consider a rubber band which is a string, assume it as a string, expand it and fix it at these 2 points O1A. It is a elastic string. So if you disturb that elastic string, you will be getting a disturbance like this, which is called as transverse vibration. So here our aim is to study what is the displacement when we vibrate it. By disturbing the equilibrium of the string at certain instant, it is allowed to vibrate transversely. So our aim is to study the vibration of the string to find the deflection, otherwise called as displacement of the string, which is denoted as y at x comma t, at any point x and at any time t greater than 0. With these following assumptions, we are aiming at finding what is the solution of one-dimensional wave equations. The assumptions very important. So the assumptions are tension T is constant, gravitational force neglected, friction is negligible, and the string is perfectly elastic. It can transmit only tension but not bending or shearing forces. One-dimensional wave equation, that is the equation governing the transverse vibration of an elastic string. The elastic string whose transverse vibration is governed by this one-dimensional wave equation, which is derived as dou squared y by dou t square, which is equal to a square dou squared y by dou x square, where a square equal to t by m, t is tension, m is mass per unit length. You should remember this equation, and what is the coefficient, what is this a square is t by m. This is very important. Solution of one-dimensional wave equation is derived by method of separation of variables, and the derivation is not required. But what are the solutions we are getting for this one-dimensional wave equation means it depends upon the value of k. With cases we derived it, and our aim is to find what is y, that is the solution of one dimensional wave equation, which is a product of x and t, x of x into t of t, where x is a function of x alone and t is a function of t alone. And solving this with cases considering k is positive, we will get one set of solution, k is negative another set of solution, k is 0 another set of solution we will get. Thus the various possible solutions of the wave equations are, it is enough if you know all these three equations. This is an important 4-mark problem. List the various possible solutions of wave equation, which is y equal to a1 e power lambda x plus b1 e power minus lambda x into c1 e power lambda at plus d1 e power minus lambda at. This is for the first case. Second case, a2 cos lambda x plus b2 sin lambda x, this is function of x, into c2 cos lambda at plus d2 sin lambda at, this is function of t. Y is equal to another case, you will get this solution, a3x plus b3 into c3t plus d3, so function of x into function of t. So three solutions we got in the derivation, and we have to choose one solution which suits the physical nature of the problem. So how to choose that solution means, in case of vibration of an elastic string, y of x comma t representing the displacement of the string at any point x, it must be periodic in t. Hence solution which consists of periodic function in t is the proper solution of problems on vibration of string. So if you see these three solution, the second solution has cos and sin function of t, which are periodic functions. So the proper solution for the physical nature of the problem is the second solution, which I am rewriting here as a2. Instead of a2 we can take it as a itself, a cos lambda x plus b sin lambda x into c cos lambda at plus d sin lambda at. So this is the proper solution for problems on vibration of strings. And two notes are given here. Note 1, if the string is initially released from rest, means you should remember that you should take the initial condition dou y by dou t at t equal to 0 is equal to 0. Note 2 is, if the string is initially in the equilibrium position, then you should take, there won't be any displacement, so y is 0 when t equal to 0. So y of x comma 0 is equal to 0. So these two note you have to remember to write the boundary and initial conditions. Examples we will see in the next video. Thank you.